Hey everyone. In this video, we're going to be going through the 7 learning outcomes and just kind of highlighting what you need to know. Just sort of big picture for each of these learning outcomes. Like, what sort of skills should you have? Maybe what sort of problems could you expect? Just for, it won't be like comprehensive, but like, I just kind of want to give you a big picture overview of what's going on in each of these learning outcomes. So for learning outcome 1, classifying differential equations and solutions, so this is really just covering everything from chapter 1. You need to, or the main things from chapter 1, you need to be able to determine whether a function or equation is a solution to a differential equation or IVP, initial value problem. And B, determine whether a given differential equation has a unique solution. Now, to determine whether a differential equation has a unique solution, the main thing you're going to look at is the theorem 1.2.1 from the end of section 1.2 that says the following. So you have some IVP, dy dx equals f of xy, and then some initial condition, y of x naught equals y naught. This is a first order linear, just a first order differential equation, ordinary differential equation. Don't worry about the parentheses. Anyway, so you have your setup, dy dx equals some expression involving x and y, and then it's going through some point x naught, y naught. And then you have some rectangular region R that contains whatever that initial condition point is, somewhere in the interior of it, not on the border, on the interior. And then the theorem says that if f and its partial derivative with respect to y are both continuous on the region, then there exists some interval contained in a to b and a unique function y of x defined on that interval that's a solution to the IVP. So in other words, if f and its partial derivative with respect to y are continuous on your rectangular region containing your initial condition point, then you can basically just find some like small little subinterval where you get the existence of a unique solution. So for example, if you had something like dy dx equals x cubed y to the fourth, then here your f of x y would be x cubed y to the fourth, and your partial with respect to y would be x cubed times 4y cubed. And so both of these two things are continuous everywhere, and therefore if it's continuous everywhere, then it's going to have a unique solution. If you had something conversely kind of like dy dx equals, let's see, what was the one from class? The one from class was y to the 1/3, I believe. So here, your f of xy is equal to 1/3 y to the negative 2/3. I don't know why I wrote 1 over y. It should be 1/3. And this is equal to 1 over 3 y to the 2/3. And then your del f del y is equal to, oh, sorry, I'm tripping. This was your del f del y. Sorry, your f is always just whatever the expression on the right-hand side of the equation is, and then your derivative of that expression with respect to y, in this case, well, I mean, there's no x's. If there was like an x here, then the x would just kind of persist. It would be treated as a constant. But here your f is y to the 1/3, and then del f del y is 1/3 y to the negative 2/3, which is 1 over 3 y to the 2/3. And so this problem here, this differential equation here, depending on what your initial condition is, may or may not have a unique solution, right? Because del f del y is not continuous at y equals 0. And so if your initial condition was, say, y of 2 equals 0, then this would not have a unique solution because it's not going to be continuous at that point. So there's no way to have a whole region where del f del y is continuous on that region, because the region has to contain the point 2 comma 0, not continuous there, because y is equal to 0. But if you were to, say, change the problem to, say, y of 2 equals 5, then this would have a unique solution. And in general, if you're looking for a region where any point on this region is going to give you a unique solution, then the region would just be, well, you have two choices. You could just simply say the upper half plane, the region y given by y is greater than 0, or if you want to be different, then you could also do the region given by y less than 0. Both this and this are rectangular regions R that would, any point that you pick in those regions would give you a unique solution to this IVP going through that point. Going back to bullet A, you need to determine whether a function or equation is a solution to a given differential equation or IVP. So remember, when determining whether something is a solution, effectively all you have to do is plug that solution into your initial value problem. So you'll have to plug it into, let's say that I found, just as a non-example, let's say that you went through the process of solving this differential equation, and then you got y is equal to x squared. Let's see, let me do y equals 2x plus 1. Okay, so y equals 2x plus 1 is maybe what you think the solution to this is. So how you could go about checking your answer, checking to see if this satisfies the IVP, is you can just go through the process of plugging this in to this differential equation, seeing if the left and the right hand sides are equal, and also checking to see if this satisfies the condition, the initial condition, y of 2 equals 5. So checking that y of 2 equals 5 is pretty straightforward. You just have to plug x equals 2 in and show that it spits out a 5. Here you get 4 plus 1, that's equal to 5. So yeah, that checks this box here. But if you wanted to check if it satisfies the differential equation, that one's not going to work out, because your left-hand side is dy dx. If you plug that in, you're just going to get the derivative, which is 2. But then your right-hand side, which is y to the 1/3, that's going to be the cube root of 2x plus 1, which is decidedly not equal to your left-hand side, which is 2. So because you're getting different things here, then that would not be a solution. If you got the same thing, then it would be a solution, right? Same thing, solution, satisfies it, so on and so forth. Outcome 2 is autonomous DEs. Before I do that, I just want to say one common mistake that I saw people do in this one. When they're showing that something satisfies the initial condition, a lot of people tried plugging the point, basically they would try plugging the point 2 comma 5 into the differential equation. You really don't want to do that. It will sometimes work, but plugging 2 comma 5 into the differential equation is just not a valid way to check that the original function itself satisfies that condition. You're basically just checking two totally different things, and sure, they're probably related in some way, but you really want to plug the points into the function itself rather than plugging into the differential equation. Anyway, autonomous DEs. Covered in 2.1, you have to identify autonomous DEs. You need to know how to identify equilibrium points and equilibrium solutions for autonomous DEs. Use that to sketch a phase line diagram for an autonomous DE, and use that to sketch solutions corresponding to various initial conditions and classify critical points as stable, unstable, or semi-stable. So if you were to, let's see, okay, so autonomous DEs are basically things that look like dy dx equals something only in terms of y, so maybe you get like y squared minus 1 or something. To find your equilibrium points and equilibrium solutions, you set this equal to 0 and solve for y. So in this case, you would get that y is equal to plus or minus 1, and so those would be your equilibrium points. And so your equilibrium solutions would be the constant functions y of x equals 1 and y of x equals negative 1. Note the distinguishment between like y equals 1 as a critical point, like that's just like a value for y, it's a y value, whereas over here y of x equals 1 is not a y value, it is a constant function. It's the function such that you're allowed, if you're to plug in any x value, it spits out a y value of 1. Okay, you should be able to sketch like phase line diagrams and stuff. So phase line diagrams, it's like, all right, so you basically sketch the y-axis and then you put all your critical points on there. And then you figure out if your derivative dy dx is going to be positive or negative on each of these, on all of the intervals broken up by your equilibrium points, right? So yeah, for various y values, like if you want to plug in like y values that are bigger than 1, y values between negative 1 and positive 1, and y values less than negative 1, you want to plug those into dy dx, which is y squared minus 1, and then see if you get something positive or negative. So if you were to plug y value greater than 1 into y squared minus 1, for example, y equals 2, you get 2 squared minus 1, that's going to be a positive number, right? If you were to plug in like a value between negative 1 and 1 into y squared minus 1, you're going to, if you had 0 squared minus 1, that's going to be negative 1, so you get a negative number. And then if you plug in a value less than negative 1, similarly, like you'll get something positive. And so now over on the left, you'll record all that information using an up arrow if the derivative is positive, and a down arrow if the derivative is negative, right? So down here, we'll use an up arrow because that derivative is positive. And then you can use this to sketch like solutions to various IVPs for this autonomous DE. So basically, if I just hand you an initial condition, like say y of 0 equals 2, then you say like, all right, well, where does 2 fit on this phase line diagram? 2 would be like up here. That's where like the derivative is positive, and so it would have this general sort of shape. So here's 2 up here, and because 2 is an equilibrium solution, 1 was an equilibrium solution. Let me put like 1 right here and 2 right here. So 1 was an equilibrium solution, so that sort of acts as like a horizontal asymptote in this. And so so the solution curve has to pass through 0, 2, right? That's the point 0, 2 right there. And because the derivative is positive there, it has to be sort of going upwards. You had something like y of 0 equals 0, then you might have something like this. Here's 0, 1, negative 1, and again 1 and negative 1 sort of act as horizontal asymptotes here. So we have to pass through 0, 0, and then we look at like, all right, well, is the derivative positive or negative? It's negative, so the slope always has to be going down. So if you were to draw something like this, that would be incorrect. It would be that would be like the correct thing if this derivative was like positive, if it was going up, but it's supposed to be going down, so the graph has to be sloping downward, so it has to look something like this. You want to make sure that this curve is like not like crashing through the asymptotes or anything. And then similarly, if you had y of 0 equals -2, that -2 would be like down here. Derivative is positive for that one, so that would be going up. So it would have to look something like this, where it's, you know, going, if I were to, you know, keep increasing, will increase up into like that sort of asymptote, will like flow into the asymptote, the equilibrium solution. And if you were to kind of reverse time and go backwards, it would be sort of decreasing without bound. And then also what happens, you know, if you have an initial condition y of 0 equals like, say, -1, well, there should have been like a negative right there, whatever. If you had y of 0 equals -1, well, -1, that's an equilibrium point, so that corresponds to this point over here. And so let's do that in red, I guess. So y of 0 equals -1. If we go through this point right here, then that means that we're on the equilibrium solution, and so we actually have to exactly be the equilibrium solution. So if you're at an equilibrium point, then the solution is just going to be the function y of x equals -1. If you want an equilibrium solution that satisfies y of 0 equals -1, assuming that -1's an equilibrium point, then the function y of x equals -1 would satisfy that initial condition and that autonomous DE. All right. Oh, and then you should also just review what stable, unstable, semi-stable is. In this case, this is unstable. This is stable because things are flowing into it. And then, you know, if you had something that looked like it's going up and then also up, so one of them is flowing in, one of them is flowing out, that would be semi-stable. Same with like the reverse of it. If they were both flowing down, then in the same in the same sort of way, you have one's flowing in, one's flowing out. All right, separable DEs. You should be able to identify separable versus non-separable. You should be able to find explicit and implicit solutions to separable DEs. Right away, you should be able to identify, or you should be able to know the difference between explicit and implicit solutions. Explicit is when you are solving for y. Implicit means you're not explicitly solving for y, but it's implied that you could technically solve for y, potentially. So implicit is basically you didn't necessarily solve for y. Explicit, solve for y. Solving IVPs for separable DEs. So if I give you something that is separable, you should be able to solve it and also figure out, like, if there's like a constant in the problem, you should be able to figure out with your initial condition what that constant is. And you should be able to identify equilibrium solutions for given differential equations. So if you have something that's separable, you might have something like dy dx equals x squared y, something like this. The idea is always to bring all the y's to one side of the equation and all the x's to the other side of the equation. And then as long as on the left everything is in terms of y and on the right everything is in terms of x, then you should just be able to integrate both sides and then get an equation relating all the variables without any differentials in it. So ln of absolute value of y equals 1/3 x cubed plus c. And then just do e to the power of both sides, and you get absolute value of y is equal to e to the 1/3 x cubed plus c. You can bring this plus c out at as a times. This is like e to the 1/3 x cubed times e to the c, just using exponent rules. But e to the c is just like a constant, so we can put that constant out in front. And we can also drop the absolute values by saying that, well, if absolute value of y equals this, then y is equal to plus or minus this. And then you can also look for like actually, before I talk about equilibrium solutions, you might have like an IVP, so you might have like an initial condition like y of 0 equals 2. So you should be able to plug in whatever that xy pair is. So y of 0 equals 2 would tell you that 2 is equal to c times e to the 0. C times e to the 0, that's just equal to 1. So that would tell you that c is equal to 2. So your solution is like y equals 2 e to the 1/3 x cubed, something like that. If you had like a somewhat more like complicated example, you might have some equilibrium solutions that are sort of lost in this process over here. You can find equilibrium solutions by saying, all right, well, this is a function of x times a function of y. Look at where the function of y is equal to 0. So in this case, like y equals 0 is an equilibrium solution. But if you had something like dy dx is equal to, let's say, like x squared times y minus 2, cubed, I guess, then here y equals 2, or let's say the constant function y of x equals 2 is an equilibrium solution. And the relevance of this is like, well, if you were to solve this differential equation, your final answer might not account for the solution for the constant function y of x equals 2. So like the function y of x equals 2, if you do this whole like separate and integrate thing, this might not be a part of your final formula for y. In some cases it will be, like the function y of x equals 0 does actually get included in this example over here. So over here the equilibrium solution is represented, but it's not always represented. So you have to be aware of when you have equilibrium solutions that are not represented in your final answer. So if you were solving the IBP dy dx equals x squared, y minus 2 cubed, and say have the initial condition y of 0 equals 2, well, you could actually just solve this one right away by just saying, well, the function y of x equals 2 is an equilibrium solution, and it satisfies the initial condition y of 0 equals 2, just because, well, y of anything is equal to 2. How do I know that this is actually a solution? Well, if you were to plug it into the left-hand side of the differential equation, that's just the derivative dy dx, or y prime. What's the derivative of a constant function? It's always 0. And then what's the right-hand side? It's x squared times y minus 2 cubed. Y is always equal to 2, so plugging that in, you're just going to get x squared times 0. So you're going to get 0 on the left and 0 on the right. Therefore, the left and right-hand sides are equal, and so it's a solution. Moving on to linear differential equations, you should be able to identify linear DEs and then use the integrating factor method to solve linear differential equations and IVPs. Linear differential equations are just going to be anything that you can put into the form like a n of x times nth derivative of y plus a 2 of x times y double prime, so second derivative of y, a 1 of x times y prime first derivative, a 0 of x times y, and equals some f of x on the right. So basically, the takeaway here, this is like your standard form of something that's linear, is that you have all of your like however many derivatives of y are in there, but you don't have anything that's like, nth derivative of y squared, or you don't have like sine of y, or just y cubed, or square root of y, or square root of y prime, or anything like that. So like y is just a linear term, and its derivatives are linear terms. So you might have something like 2y plus 3x squared y prime, or let's say y double prime, is equal to cosine of x minus xy prime. So this would be something that's linear because all of the y terms, or like y and its derivatives, are all just, first order terms. And the coefficients of y, as well as like the, this, you could think of this as like a zeroth derivative of y, because like y is just not there. So all of these coefficients are just basic functions of x. There's no restrictions on the functions of x. The only restrictions are really restrictions on y. But you don't have like, 3x squared y as the coefficient of y double prime or something. So this would be linear. This would be second order linear. Something that's first order linear might be like x squared y prime plus 2x y equals 5 cosine of x, something like that. Yeah. So first order, so this is first order linear. And whenever you have first order linear, you can use the integrating factor method to solve this differential equation, right? So the way to do that would be, let me make this like a little bit, maybe a little bit more complicated. Let me just get rid of this x squared term right here. Or maybe I'll make it an x and make that an x squared. Okay, yeah, so something like this. So if you want to solve a first order linear DE, you want to first normalize it, so make sure your y prime term doesn't have anything in front of it. So you'd have y prime plus 2x times y is equal to 5 cosine x all over x. So we're just literally dividing everything on both sides of the equation by x. You get this. Then you figure out what's your integrating factor. It's going to be the function mu of x equals e to the integral of whatever the new coefficient of y is after integrating, after normalizing. So this would just be e to the x squared. In some situations, you might be able to simplify this. Like if you had e to the ln of something, then you could like cancel the e to the ln's. In this case, like there's no ln, so this is just as simplified as it gets. And then you would multiply both sides of the equation by that integrating factor. The left-hand side should always simplify as just the derivative of whatever your integrating factor is times y. You should always check this, because if you check this and this is not equal to this, then that means that you did something wrong up here, right? Maybe you forgot to normalize by x, maybe you integrated something incorrectly, but something went wrong if you see that this is not equal to this, right? So to check that this equals this, just do the product rule, because we're just reversing the product rule here. Product rule says the derivative of e to the x squared times y is, well, e to the x squared times y prime, and then plus the derivative of e to the x squared times y. What's the derivative of e to the x squared? It's e to the x squared times 2x, which just happens to show up over here. So this does reverse the product rule correctly. Your right-hand side, in this case, we're not going to be able to solve this very easily, but like, assuming that you get something on the right-hand side that you can actually integrate, your next step would just be, integrate both sides with respect to x. And then your left-hand side is just going to be e to the x squared times y. And then your right-hand side is just going to be whatever that antiderivative is, plus c. And then you can just divide both sides by e to the x squared. Remember that like c over e to the x squared, that's not just equal to a constant c. This has a variable in it. Constant divided by like a variable is not a constant, so you can't treat it like that. So that's another common mistake that I kind of see with these things, so just keep that in mind. With exact differential equations, you should be able to identify them using the check of the mixed partials that we always do, and then you should be able to solve these exact differential equations and their associated initial value problems. To check if something is exact, you have something like m dx plus n dy equals 0. You should just take, all right, so there's a dx right here, so what you want to do is like do the derivative with respect to whatever the other variable is to get the mixed partial there, and then do the derivative with respect to the other variable over here. So here there's a dy there, so do the other derivative, here with respect to x, and then see if you get the same thing for both of these mixed partial derivatives. If you get the same thing, then it's exact. If you get something different, it's not exact. So if you had like something like x squared dx plus 2xy dy equals 0. So here x squared dx, you want to do a partial with respect to y because there's an x right here. Derivative of x squared with respect to y is just 0. Over here, we want to do a derivative with respect to x because there's a dy right there. That derivative would be 2y, so this is not exact. But if I were to change this problem to x squared y squared, actually, no, that's not going to work. Let's just make it, actually let's do x squared plus y squared. I think that would work out. So x squared plus y squared, what is that derivative with respect to y? Well, derivative of x squared is 0, derivative of y squared is 2y, and so this is actually going to give us equal mixed partials, right? From there, you can either integrate this guy to figure out what your f is, and then take a derivative of that, set it equal to 2xy to figure out exactly what your f had to be, or you could do the reverse, integrate 2xy dy, and then take a derivative with respect to x, set it equal to that. Or you could do, you could like sort of integrate both of those things, collect and combine all like terms for both things, and then set things equal to each other. I kind of don't like that one because I don't really like the whole collecting like terms thing. I think it messes a lot of people up. Everyone that did it on the last week's quiz, and there were people that tried, everyone that tried messed it up. So I don't like teaching it that way. How I like doing it is integrate one of them, or let me say integrate this guy first. Let's do integral of 2xy dy, and that's going to be equal to whatever our f is. So that's going to equal 2x times integral of y is 1/2 y squared. And it's like plus a constant, but it's really a constant with respect to y, so it could have some x's in there, so it's like plus g of x. All right, so that's your f. Then you need del f del x to be equal to this guy over here, x squared plus y squared. And then, so what is this guy over here? Let's simplify the 2, so that's xy squared plus g of x. And so what's del this guy, del f, or sorry, with respect to x, derivative of xy squared is just y squared, and then plus g prime of x, set that equal to that x squared plus y squared that we had. This y squared and that y squared cancel out, and then you get that g prime of x is equal to x squared. And so you can integrate with respect to x, and then g of x is just going to be the integral of x squared, which is 1/3 x cubed. And so your f is equal to xy squared plus g of x, or plus 1/3 x cubed, right? Now that's not what your solution is. Your solution, well, if this differential equation is exact, then that means your left-hand side is basically just the derivative of whatever your f is. So this left-hand side is really just saying the derivative of xy squared plus 1/3 x cubed is equal to 0. And so how do you solve? Well, from there you could just integrate both sides with respect to x, and you get xy squared plus 1/3 x cubed is equal to 0 plus a constant. And so this would be what your solution is. You can then, plug in whatever your initial conditions are to solve for c. All right. The substitution method, you need to be able to identify DEs that can be solved with the substitution, and you need to be able to solve these DEs using the proper substitution. So if I were to hand you something like x squared y dx plus xy squared plus y cubed dy equals 0, just something random like that, you should be able to tell me whether or not you can solve this DE with a substitution. So this example right here, this is a homogeneous differential equation because the degrees of everything, if we were to, everything is going to be like a degree 3 term, right? Y cubed is degree 3. Xy squared is also degree 3 because you like sort of add the degree of the x's and the y's. It's like x to the 1 plus y to the, or times y to the 2, you get degree 1 plus 2. This is also degree 3 over here. So this is homogeneous. So if you're to do either u equals y over x or v equals x over y, both of these substitutions, either of these substitutions would reduce this down to a separable differential equation. So you should be able to do that whole separation, separate all the, the u's from the x's or the v's from the y's, or however you do it, and then sort of integrate both sides and proceed. This one right here, this might reduce, this thing right here might reduce this to something that is separable, but being separable doesn't necessarily mean that it's easy to solve, because you might separate the variables and the left-hand side is something that's very difficult to integrate, and the right-hand side is, maybe the right-hand side is a little easier to integrate, but the left-hand side seems impossible to integrate. So I'm not gonna say that you should try this one exactly, right? If you were to just do this one, you might get something that's just very difficult to integrate, but it definitely will be separable. That will always happen. You should also be familiar with Bernoulli's equation. So that would be something that's almost first order linear. So if you have something like dy dx plus x squared y is equal to 2y to the 4th or something. So this is not linear because this y to the 4 term right here is not a linear term, right? So the y to the 4th is not a linear term, so it's not linear, but it is Bernoulli. Bernoulli says you have dy dx plus something times y is equal to something times y to the n, and n can be whatever you want. So if you have something that's Bernoulli, then your substitution is going to be u equals y to the 1 minus n. So in this case, it would be u equals y to the 1 minus 4, or just -3. And then typically you would solve for y and then sub that in. So here, y would be equal to u to the -1/3. Just raise both sides to the -1/3 power. So the -3 and the -1/3 cancel. And then what would dy dx be? be negative 1/3 u to the negative 4/3 times du dx. And then you can sub all this stuff out. And then once you sub all this stuff out in terms of u's and du dx's, then you should be able to simplify it to something that looks linear. And then once you get something that's linear, then you're going to want to do the integrating factor method to actually solve it. You might also see something that looks like dy dx equals some function of ax plus by plus c. So maybe you have like 3 times 2x plus 4y plus 5 cubed plus 7. So here we're like plugging into 3z cubed plus 7, and we're plugging in 2x plus 4y plus 5 into it. So in this case, the substitution that you'll do is u equals 2x plus 4y plus 5. You'll sub that in, and then that should give you something that's separable. You should also figure out like what's your du dx. Du dx would be, so you just take derivative with respect to x of both sides. Derivative with respect to x of u is du dx. With respect to x of 2x, that's just 2. Derivative of 4y with respect to x is 4 dy dx. And derivative of 5 is 0. And then you'll replace dy dx with something in terms of u. And you'll replace this term right here with just u. So you'll get like 3u cubed plus 7 on the right, and then whatever you get when you solve for dy dx in this equation on the left. Oh yeah, I didn't mention like how you would do that over here, but like, you know, if you were to do v equals x over y, you want to solve for x is equal to v times y, and then do a product rule on this so they can sub out dx over here. So we're trying to like replace dx with something, so compute what dx is. That would be v dy plus y dv, just doing a product rule. And then you can replace all of your x's with vy's and all of your dx's with these things, and then you should be able to separate everything and then integrate. All right, and then the last thing is Euler's method. So this one is just, you just need to use Euler's method to approximate solutions to IVPs. So if I give you something like dy dx equals 2xy, and maybe say y of 1 equals 2, then basically you just use the tangent line. Oh, I should tell you what I want you to approximate. Approximate, say, like y of 2 using step size of h equals something. So maybe I do like step size of a half. If I do a step size of a half, then that would mean that there's like 2 steps to do here, because we're going from x equals 1 to x equals 2 in 1/2 size increments. So 1 to 1/2 to 2. Sorry, 1 to 1.5 to 2. So what you do is at each point, so at your initial condition point, you're at the point 1, 2, because y of 1 equals 2. What's your slope going to be? It's going to be 2 times 1 times 2, right? 2xy, you just plug in your x and y values. So the slope would be equal to 4 in this case. So approximate next y value is going to be whatever our previous y value is. So the previous y value plus our slope, which is 4 times our step size, h. So it's like our previous y value plus m times h. Like y sub, this is like y sub like k minus 1 times m sub k minus 1 times h. Whatever your previous y value is, whatever the slope at that previous y value is, and then times your step size. So 2 times 4, 2 plus 4 times a half, that's 2 plus 2, that is equal to 4. So our next y value should be approximately 4. So our next point would be 1.5 comma 4, because we increment our x value by half, and then we figure out what our next y value would be. And then at that point, your slope is going to be 2 times the x value times the y value. So that's 2 times 1.5 times 4, that's 3 times 4, that's 12. And so our approximate next y value is previous y value plus slope times step size. So that's 4 plus 6, so roughly 10. Okay, so that would tell you that y of 2 is roughly equal to 10. Okay. Now, this is like a really big step size, so this is probably going to be a very inaccurate answer, but this is like the general procedure for how you would do it. Right? If you did a step size of like 1/4, well, if you're going from 1 to 2 with a step size of 1/4, then you'll have 4 steps to do. All right? If you did like 1 to 5 with a step size of 1/2, then you would have like 8 steps to do. Right? 1 to 5, that's like a distance of 4, and with a step size of 1/2, you need to do it 8 times. Right? But each step is going to be like this same computation of, all right, what point are you at? What's the slope at that point? And then the y value is going to be previous y value plus slope times step size. That gives you your next y value, and your next x value is just the old x value plus whatever your step size is. So plus a step of like 1/2, we're at 1.5 here. All right. I can't really think of anything else to say here, so yeah, that's it. So, I should maybe give you a little bit of guidance with sort of pace as far as like what you should sort of be shooting for by the end of each exam. So let me go to the learning outcomes document, look at sort of grades that you could get. So there's 18 learning outcomes in the course, and then there are 3 exams and a final. So let's just say that over the course of the semester you get like 3 LOs on quizzes. Actually, no, instead of talking about it like that, let's just think about it in terms of like, all right, you want to get to a certain number by the end of the semester. Let's say that you're shooting for an A, right? You're shooting for 16 learning outcomes over the course of the semester. Well, you have 4 exams, and so, and like a bunch of quizzes too. So a good pace to be on to get to 16 learning outcomes completed by the end of the semester would be roughly 4 LOs by the end of exam 1, 8 by the end of exam 2, 12 by end of exam 3, and then 16 by the end of the final. So that's like a rough pace that you might want to be on like an A pace, right? So this exam, it has 7 learning outcomes on it. And so if you like mastered 1 on the quizzes, then you might try to shoot for 3 on this exam to be like on an A pace. Maybe you don't have any completed so far. That's totally normal. About half the class still hasn't mastered anything, and that's fine. But if you don't have any, maybe shoot for like 3, maybe 4, and then try to pick it up like on some of the future quizzes to bump up that pace. So prioritize your studying too. Like if you're like really not feeling comfortable with the substitution method, for example, then maybe spend more time on separable differential equations just to make sure that you get it. Spend more time on autonomous DEs. Spend more time on like the low hanging fruit just to make sure that you get those ones, right? If you don't like the substitution method, then well, you need to get if you're shooting for an A pace, then that kind of gives you like 2 learning outcomes of leeway, or there's 2 throughout the whole semester that you don't necessarily need to get. And so every now and then you might just be like, I don't really know how to do this. I don't really want to learn how to do this. I'm going to try and learn more deeply the other things in this class or something like that. That's an option that's available to you. I'm not necessarily saying I recommend it, but it is, something that you're able to do. That said, I would, if you are going to maybe prioritize learning outcomes 1, 2, maybe 4 and 5 or something, maybe those 4, it still might make sense to spend a good amount of time on learning outcomes like 3, 6, and 7 just to kind of give it a shot and make sure that you kind of know what's going on. So make sure that you really know what's going on with the ones that you kind of want to prioritize, maybe 1, 2, 4, and 5, and maybe have like kind of an idea on the other ones so that if you have extra time on the exam, that you can at least give those an attempt and get a little bit of feedback on those for future attempts or something. Because, the way that this is all structured, it's like feedback is very, I think, valuable in this sort of setup. Because, if you attempt something and that'll give you an idea as to like what you really are understanding about it and what you can do better for future attempts, and giving you a better chance at mastering something on a future exam. So anyway, I think that's all for now. So thanks for listening. I hope this was helpful. If you do think this is helpful, like this was a helpful format, I can do something similar for like the exam 2 outcomes. So if you do think that it's helpful, please let me know. If not, I could just make it more like problem focused for future exam reviews, just doing random problems and stuff like that. But yeah, let me know. Anyway, good luck studying, and I'll see you guys later.